Hello everyone, this is LemoHX and a normal pre-university student. And today I'm going to record a video series about writing Haskell, writing algorithms in Haskell. So actually, why I decided to use Haskell? Because Haskell is a pure functional programming language, and the advantage of pure functional programming language is when you're writing things, there are no side effects. So for example, change of this value won't affect that value, not like C language. So actually, when you talk about algorithm, the first algorithm you probably learn is binary tree. So let's just look what is a binary tree. Have a look. So this is a binary tree, binary search tree. So what is the advantage of binary search tree is first you have a unorganized, let's say array, and then you can put in array with an algorithm in sequence, and then follow the rules that they how to take out one by one element. You have the sorted, then you have the sorted array. So just let's start programming. Okay, so here we see is Haskell. I just installed this Haskell on my Ubuntu based on my WSL. So here I don't recommend you to install Haskell on Windows. First, the GNU libraries will mess up your Windows, and second, the GHC costs a huge amount of space, and then something does not work on Windows. I've tried before, so I choose WSL, but you also could choose something like Docker Compose, or virtual machines. So here we are. This is the main.hs, like main.c or C, just main.hx. And about how to learn Haskell, there's a tons of series you can watch. So I'm just going to write some algorithm. So here we are, the main. You can see the main signature is IO. What is IO? Just like input output. Basically, it's just a monad with side effects. Well, but this is just a case that we must use that. So main IO here is to some func defining lead point lead.hx. So here I'm gonna change it. First, if you want to do some competition like OI or ASM, the first thing you need to do is get the input from the CLI. So let's get some input from CLI. Main equals to read. So I get line. First I get the input, and then I'm using this symbol to get the words, and then I separate the words using a read, and then map all of them. So I get more or less everything from the CLI, and then I need to try to put it out. Well, this. I need to show what I've read it. For example, here I just do a 1 + 1 is 2. So read, well, how about read it? Because read this name is already used. Read it, 0 plus the read it 1. Okay. So we can use stack run. Let's take some time for compiling the first time. One and one should be give me a 2. Okay, so here we are. 1 + 1, you can see here first I get line and separate by words, and then read and then map to all of the words, and then you get the, how to say, first you convert the input algorithm, like something like string, IO string. Let me see, IO string, and then combine it to the words. So you separate the IO string by space or something, like, and you get like 1 and a 1 string, and then you use read to parse 1 and 1 to something like integer, and then you just show the first plus the second. Okay, so now I'm going to just write a simple binomial search tree. So what is the binomial search tree? We can see on the Wikipedia, or just randomly look at picture. The tree here starts with the roots, and then with 2 only leaf, and then on leaf they have some value, and the leaf at end of the leaf is another root, and root have another 2, and here have 1 only, but you can have 2. You can see. So I just want to write that in Haskell. So in order to do that, we can start using a data type, data bst a. Well, this is for a higher quantity type, but you don't need to know, or you already know, just don't want me to explain again. The note, we need a note, and then start with, I already said, first the root have an element, and then left and right is another whole tree. Okay, now I can see my BST. Well, top not available. Why? Just because they're just dumb. Deriving. I need the deriving show show you the detail, and then derive an EQ for just normally I just derive an EQ, and then we have the BST. Now more or less already work, but we need we need to know how we insert an element into the tree and their behavior, and then we have 3 ways to walk through the tree. So they have like ordered walk, front walk, back walk, and the search. So let me just show you what are the means. So order walk and BST. There's 3 ways to walk. You see, a pre-ordered using the parent first, and then left, and then right children in order. With the left, and then the parent, and then the right. And post order using the left, and then the right child, and then the parent. So I need to implement that. So by implementing that, there are 10,000 of trees, but their behavior is more or less the same. So we can define a type class tree T, where they all, for every kind of trees, they always have insert. Insert need the order to a tree and the element to the tree, and then return the tree itself. Actually, this is a copy of the tree, not actually insert to the tree, because it's a pure language. It just, the tree, you add an element and return the whole thing, not only the, just put this on the tree and then keep it. And you have an order walk, so you have T, A to the array. Because after the walk, it just leave you an array of the sequence, which node have you walked. The same. I'm just going to copy that. Back, and then have back, order, front, and back. And then we have a search. So on the binomial search tree, the insert rule is smaller goes left, bigger goes right. So using that rule, we can find more or less what we look at. For example, we have a tree like, let's find an example of a binary tree. Binary tree. search tree, binary search tree better. Binary search tree, so you can see, yeah, this is a good binary search tree. So let me think, I'm looking at 6, so my root is 8. 6 is smaller than 8, so I go to the child, left child. Okay, left child is a 3, a root is a 3, and 6 is bigger than 3, so we go to the right. And here is the 6 we look at. So for example, we say I'm searching at 14. 14 is absolutely bigger than 8, so we go to 10. And bigger than 10, we go to 14. So here we are. So using this kind of rule, we can search elements by using a binomial search, a binary search tree. So let me just write the search method. Search is you need ordered, and then you need a tree, and then find the element, and then return a bool if it's in the tree or not. And now we just try to implement that to our BST instance tree BST, where, well, ignore, where the insert to a empty tree, you just get nothing. Well, you just get the tree with the value. Yep, and then the value, and then the big empty. Okay, and then you insert to a normal tree using the pattern matching sugar. You can do like that, left, X for root, and right for the right. And then you have value. And then using the guardian, if V is smaller than the X, go to B node, insert L, V. So you insert this to the left, and then if the left is still bigger, to the left, because this is a recursive. And finally we arrive the end, and then otherwise goes to the right. So we keep the same part as the L, and we insert to the right. Okay, so we finished the insert, so we can actually have a look how this insert will go. Fine. So first, I have a tree. Well, just load the stack, load the GHC, and then we can show you, well, the empty, sorry, my mistake. Load GHC. Okay, we loaded the GHC. So let's see, we have a tree equals to the binary tree, BST, and it's a empty tree, so be empty, and that is. And we insert 10 to T. So we can see the result is B node, B empty, 10 empty, the 10 as a root, as we expected. And then we can do something like that. So if you let B equal this one, and then we insert B, a 3. The 3 definitely is smaller than 10, so it will go to right, left. You see, here we have the B node. In the left node, that starts with a root at a 3, and the middle is a 10, and the right is still empty. And for example, if I do that, so insert C, a 12. 12 is bigger than 10, so it goes right. Yeah, so you can see this tree works well. And then we need to write the order walk, front walk, and the back walk our algorithm to try to walk the tree. So from the order walk, empty, it shall give you an empty array, and then order walk will give you order walk L plus the X with the order walk R. So you can see the order walk is just from left to the middle to the right. And then I need the front walk. Is equal to, so front walk is the root at the first, and then walk to the left and walk to the right. So like this. Front walk L plus the front walk R. And then the last thing is back walk. So the back walk is first left and then right, and then go to the root. Okay, so now it will more or less. Okay, sorry, I forgot the empty case. So I need to make sure that empty case is implemented. Just wait a minute, and then okay, and this is to front, and that is to back. So actually there are 3 ways of walking, and then after I finish the walking is the search. So let me just test if the walking works. So I have this. I need to take this, copy, and then load my new change of the file. And then I just using this. Well, let a tree is equal to this. And then we just try to print out the tree. You can see this, and then we order walk the tree. You can see first 3, and then 10, and then to 12 is order from left to middle to right. And then we use the front, the tree. You can see the 10 as goes front, and then the left, and then the right. And use back walk the tree. And you can see. First the left, and then the right, and then the root. More or less makes sense. And then we write the search method. So nothing and searching value is absolutely false. So searching a normal tree, first we look at if the root is the answer. Sorry, I forgot the v. If v equals to the root, directly returns true. If the v is smaller than the root, then we can look at on the left. If the v is bigger than the root, we can look at on the right. And then the recursive is, so you look at left, and if left doesn't have, you look at left. If left is empty, then return false. That's why we covered all the case. And then I just try to copy the tree again and load my new change of GHC. Let t equals that kind of tree. and let's search tree. Shall we search 13, my favorite number? No, it's not in the it's not in the tree. And if we search 3, yeah, it's on the tree. So here we have a type class of all the methods we need to use when we're using a binary tree. And here we have a data type for the tree. You can see empty and a note. And here is a method we implemented for the tree. And here just a normal way to getting the command line input. And well, in next class, in next video, I'm going to talk about another balanced tree called red-black tree. Maybe some people already heard about this tree. In Haskell, implement a red-black tree is super easy, but you couldn't remove the element from the red-black tree if you implement it easy, because in the red-black tree they have a double black node, and that is quite hard to handle. So I will just write a mutable red-black tree. So thank you, and if you like my video, please subscribe and thumb up. Bye.